In this example of shear and moment diagrams, we again have a simply supported beam, 80 inches long, with a concentrated load of 80 pounds at the midpoint and a uniformly distributed load of 10 pounds per inch on the right half of the beam. So we will use the same positive sign conventions as we have seen in the previous lecture, where a shear force to the left of the cut going up is positive, to the right of the cut coming down is positive, and then the moments also, which are shown in the figure. So the first thing to do, as always, is to find out the support reactions. Let's call this support A and this support B. So to find out the vertical reactions at A and B, R sub A and R sub B, you can do it simply by taking moments about any one of the supports. You will find out that RA is 140 pounds and RB is 340 pounds. You can work that out fairly easily. So once we know that, let's start with drawing the shear force diagrams. We'll use a very similar approach as we have done in the previous example, and we will use that's bending moment, positive and negative. Right, so like we did earlier, we'll start from left to right. We'll draw the free body diagram of this beam with a cut slightly away from A, to the right of A. You know that the reaction of A is 140 pounds, that's acting up. 140 pounds acting up. Therefore, an internal shear of 140 pounds should act down to the right of the cut, which is positive as far as our sign convention is concerned. Therefore, the shear force here is 140 pounds. Now, until the concentrated load of 80 pounds, there is nothing that's happening in this beam, so we can do that connection right there. Now, if we take 140, if we take a cut slightly to the right of the concentrated load of 80 pounds, slightly to the right of this load, ever so slightly to the right of that load, so that the effect of uniformly distributed load is not evident at that point. It's infinitesimally small, so it's only 80 pounds. Then you will have a concentrated load of 80 pounds coming down, 140 going up, 80 coming down. That will result in a net shear of 60 pounds to the right of the cut. That's also positive. Therefore, we have a positive shear here of 60. So this value is 60. So we have 60 pounds. So that's the value of 60 right there. Now, if you go to the right support, just to the left of right support, you will have 10 times 40. So the effect of the uniformly distributed load acting, so 10 times 40, that's 400 pounds, and then that is 480 and 140. Therefore, there has to be a 340 pounds acting at B to the right, and it should be acting upwards to counter the 400 plus 80 minus 140. So it has to be acting up. Right of the section up is negative. Therefore, you have a shear force of 340 pounds here. Then you connect the 60 and 340 straight line. That is your shear force diagram. Okay, so we can check it from the other end also, from B. We know there is a 340 pound load. That's the support reaction. Then to the left of it, there has to be a 340 pound left of the cut acting down. Left of the cut acting down is negative. 340 is what we got. Therefore, we have confirmed that our shear force diagram is correct. I don't know why I wrote here bending moment. It has to be shear force. Okay, once we do the shear force, now we can move on to the bending moment diagram. Okay, so I will extend this one here. To do the bending moments.
I can learn to understand you much better if I...
That's a bending moment. Positive, negative. Okay. So first part, fairly easy, rectangular, that is 140 times 40. That's what you have, 140 times 40, which is 5600 pound inches. That is going to be a positive. So there is 0 here because look at the support, there's no moment. And then by the time you get to the midpoint of the beam, you have a 5600 pound inch bending moment. Because the shear force is rectangular, the bending moment has to be a linear variation. So this linear, we'll show it as curve, it has to be linear. That is the, I'll just write it linear. So 5600 pound inch is the bending moment here. Now, remember, there is an inflection point in your shear force diagram, so that has to be another critical point right here because there is a change here. So what happens? You have that area 60, and then what is that distance? So let's call that distance x, and you can use these two similar triangles. This is one similar triangle. This is one similar triangle here. So if you do the altitude over base, it's 60 over x, and this is another similar triangle here. So if you use those two similar triangles again here, altitude over base would be 340 divided by 40 minus x. If you solve, you will get x as 6 inches. So this distance x is 6 inches. Therefore, you can get this area as half times 60 times 6, which is 180 pound inches. So 180 pound inches is the additional, again remember that also is the positive side, that is the additional moment that has to go on in that section. You have 5600 here, there has to be 180, so you will get to 5780 pound inch. Now remember, because that is a triangular variation, your curve in that range is going to be parabolic. So that is a parabolic relationship. And then from 5780, you can do this part now, which is half times 34 times 340, and you will get that as 5780. That's going down, so it's negative, which will take you down to 0, and remember that also has to be parabolic. That is 0 here, and so these two sections are parabolic. It's a good idea to write it down, because if you're drawing a bending moment diagram in the exam with hand, you might not be able to do it correctly. There are software that will do it for you, that'll pick it up correctly, but if you're drawing it by hand, it's a good idea to make a note of it. So again, here is the shear and bending moment diagram for that case. I'm sorry. So again, just to recap, we are going from left to right. We take a cut, find out the shear forces, keep on going further to the right until you get to the end of the beam, finish the shear force diagram, take the area or under the shear force diagram at different sections, and then that is the change in bending moment, and then you plot the bending moment diagram. So here is another simple example for shear and moment diagrams.